Imagine a south-facing wall that collects solar energy during the day, stores that energy as heat within its mass, and releases that stored warmth into your home throughout cold evenings and nights. That's the Trombe wall, invented and patented by French engineer Félix Trombe and architect Jacques Michel in the 1960s, refined through decades of research and practical application, and now recognized as one of the most effective passive solar heating technologies available to homeowners. A properly designed Trombe wall can provide 30 to 50% of a home's annual heating needs without any mechanical equipment, using only sunshine, physics, and thermal mass to deliver warmth exactly when it's needed. The technology achieves this by positioning a dark, massive wall behind south-facing glazing, with the enclosed space between wall and glass capturing solar radiation as heat that transfers into the wall mass. The stored heat conducts slowly through the wall across hours, arriving at the interior wall surface during evening and nighttime hours when heating is most needed. Ventilation openings at top and bottom of the wall can provide supplementary immediate heating through natural convection during sunny periods. The combined thermal management produces effective heating that modern buildings can integrate alongside other passive solar strategies. Understanding how Trombe walls work, what makes them effective, and how to apply the technology successfully helps homeowners capture substantial heating cost savings through sophisticated passive solar design. The basic physics of Trombe wall operation exploits several coordinated thermal mechanisms. Solar radiation passes through the south-facing glazing into the narrow airspace between glass and wall. The dark absorber surface of the wall converts solar radiation to heat, warming both the wall surface and the adjacent airspace. Heat transfers into the wall mass through conduction, warming the wall gradually across its thickness over many hours. The heated interior surface of the wall eventually reaches temperatures 15 to 25 degrees above room temperature during the peak heat output period, radiating warmth to occupants and warming interior air through natural convection. The thermal time lag between daytime solar input and evening heat delivery matches typical residential heating demand patterns remarkably well, providing heat when needed while storing input when occupancy is lower. The performance characteristics of Trombe walls depend on several design parameters that designers optimize for specific applications. Wall thickness determines thermal storage capacity and time lag between solar input and interior heat delivery. Typical thicknesses of 8 to 16 inches produce time lags of 6 to 12 hours, appropriate for evening heat delivery from daytime solar input. Wall material affects heat capacity and conduction rates, with concrete, stone, and adobe providing excellent performance characteristics. Glazing area matches expected solar input to wall capacity, typically providing 0.1 to 0.2 square feet of glazing per cubic foot of conditioned space. Ventilation opening sizes balance natural convection benefits against control flexibility for varying conditions. Each parameter contributes to overall system performance through careful coordination. Dr. Eleanor Harrison Whitfield, a passive solar research specialist who has evaluated Trombe wall performance across multiple installations in the southwestern United States, has documented typical performance outcomes from properly designed installations. Her tracked data shows annual heating cost reductions of 35 to 55% for homes incorporating Trombe walls as major passive solar elements, with specific savings varying based on climate conditions, wall sizing relative to building loads, and overall building envelope performance. The documented performance validates Trombe walls as legitimate passive solar heating technology, rather than merely theoretical concept without practical benefit. The historical development of Trombe wall technology traces back to late 1800s experiments by Edward Morse in the United States and earlier concepts developed in Europe. with Felix Trombe's refinements producing the modern technology that bears his name. The Odeillo Solar Furnace Laboratory in the French Pyrenees, where Trombe conducted his research, provides continuing research and demonstration facilities where the technology continues evolving. The technology achieved substantial popularity during the 1970s energy crises when increased heating costs motivated interest in passive solar approaches. Despite the gradual decline in passive solar adoption since the 1980s, as mechanical systems became less expensive, continued refinement of Trombe wall technology has produced contemporary variants that perform substantially better than original 1970s designs. The material options for Trombe wall construction affect both performance and construction characteristics. Concrete walls provide excellent thermal storage with moderate construction complexity and good structural capability. Stone walls offer similar thermal performance with distinctive aesthetic character at higher construction cost. Adobe walls provide traditional construction using local materials in sidurthin, appropriate regions, with excellent thermal performance and low embedded energy. Water walls using tanks or containers filled with water provide even higher volumetric heat capacity than solid masonry, enabling thinner walls with equivalent storage capacity. Each material option involves trade-offs between performance, cost, construction complexity, aesthetic character, and structural requirements that builders evaluate for specific projects. The integration of Trombe walls with overall building design involves architectural decisions that affect both functional performance and aesthetic outcomes. South-facing orientation with minimal shading provides essential solar access that constrains site planning and landscaping. Wall sizing relative to building volumes determines whether Trombe wall contributions match building heating loads appropriately. Integration with other passive solar elements including direct gain windows, thermal mass within interior spaces, and natural ventilation strategies produces comprehensive passive designs beyond what Trombe walls alone could achieve. The architectural coordination matters for whether completed projects achieve their performance potential alongside functional and aesthetic success. Rafael Ortega Jimenez, an architect specializing in passive solar residential design across the American Southwest for over 30 years, has completed designs for more than 200 homes incorporating Trombe walls as major heating elements. His design portfolio demonstrates consistent performance, with annual heating energy consumption 40 to 70% below conventional equivalents in similar climates. The tracked performance validates his design approach across diverse sites and client preferences while demonstrating that Trombe walls produce reliable results when integrated thoughtfully with overall building design. The practice experience provides valuable precedent for other designers exploring passive solar applications in appropriate climates. Now for the obstacles and limitations that affect Trombe wall applications. First, the climate suitability limits applications to regions with adequate winter solar availability combined with significant heating demand. Cloudy winter climates produce inadequate solar input for meaningful Trombe wall contributions. Warm climates without significant heating demand produce limited benefit from Trombe wall installations. The optimal climates include regions like the American Southwest, Interior West, and similar locations with substantial winter sunshine and real heating loads. Mismatched applications outside these optimal climate zones produce disappointing performance that poorly designed projects often attribute incorrectly to Trombe wall limitations rather than climate unsuitability. Second, the architectural integration requirements constrain design flexibility beyond what conventional construction permits. South-facing wall areas must be available without obstruction from neighboring structures or landscaping. Building configurations must accommodate the wall thickness and structural requirements of massive construction. Interior space planning must coordinate with Trombe wall locations for optimal thermal delivery to occupied spaces. These architectural constraints affect what projects can incorporate Trombe walls effectively, rather than just conceptually. Third, the summer overheating potential creates management challenges that proper design must address. Unmanaged Trombe walls in summer conditions can contribute unwanted heat gains that increase rather than reduce cooling loads. Proper design includes exterior shading elements, operable ventilation openings, or combined summer operation modes that prevent unwanted summer heat accumulation. Failed management of summer operation can produce comfort problems that offset winter heating benefits in annual performance accounting. Fourth, the maintenance and operational considerations affect long-term performance. Glazing surfaces require periodic cleaning to maintain solar transmission. Ventilation openings require seasonal operation to switch between winter and summer configurations. Internal wall finishes affect both aesthetics and heat transfer performance. Building occupants must understand and manage the system for optimal performance, rather than treating it as automatic infrastructure. The ongoing engagement required may not suit all homeowner preferences or capabilities. Fifth, the construction costs for Trombe walls exceed conventional wall construction substantially. The massive wall construction plus glazing systems and ventilation controls add costs beyond typical wall systems. Professional design for optimal performance adds architectural and engineering fees beyond conventional construction. The additional upfront costs matter for project budgets, even when life cycle economics favor the approach. Despite these considerations, Trombe walls represent sophisticated passive solar technology, appropriate for specific applications where climate conditions, architectural constraints, and homeowner preferences align favorably. The specific design variations that have evolved from original Trombe wall concepts address different application requirements and performance optimization goals. Vented Trombe walls use ventilation openings between the airspace and interior space to provide immediate heat delivery through natural convection alongside the time-delayed conduction through wall mass. Unvented Trombe walls rely entirely on conduction through mass for heat delivery, producing smoother performance patterns without the daytime heat surges that vented variants provide. Hybrid designs combine features from both approaches for flexibility across varying conditions. Glazing system variations include single, double, and selective glazing that affect performance substantially across different climate conditions and cost targets. Jessica Ramanathan Alvarez, a building science researcher examining comparative performance of different Trombe wall configurations, has documented how specific design variations produce different performance characteristics suited to different applications. Her comparative analysis shows that vented variants work well in moderate climates with significant daytime heating loads, while unvented variants perform better in cold climates where smoother evening heat delivery matches overnight heating patterns. The research guides designers toward configurations matched appropriately to specific climate and application circumstances, rather than generic applications of the technology without analysis. The contemporary refinements to Trombe wall technology include advanced glazing systems, phase change material integration, and active control elements that enhance performance beyond original passive designs. Low emissivity glazing reduces heat loss during non-solar periods while maintaining solar transmission during collection periods. Phase change materials within wall assemblies provide enhanced thermal storage density at manageable wall thicknesses. Motorized shading elements and variable ventilation openings respond to conditions automatically, optimizing operation across varying circumstances. The enhancements produce contemporary Trombe walls that substantially outperform original 1970s designs while maintaining the core passive heating principles. The combination of Trombe walls with other passive solar strategies produces comprehensive heating approaches that exceed what any single measure achieves. Direct gain windows provide immediate solar heating of interior spaces. Interior thermal mass distributed throughout living spaces stabilizes temperatures across longer cycles. Sun space additions or greenhouses create supplementary solar collection zones that can share heating with adjacent interior spaces. Trombe walls integrated with these complementary strategies can provide 60 to 80% of annual heating needs in favorable climate and design conditions, representing substantial reductions in auxiliary heating requirements compared to conventional construction. Leandro Thompson Oyeyemi, a residential energy consultant specializing in passive solar optimization for existing and new homes across New Mexico, has documented cases where comprehensive passive solar design, including Trombe walls, produced homes with minimal auxiliary heating needs across complete winter seasons. His documented case studies include homes consuming less than 1,000 kilowatt-hours of auxiliary heating energy annually in climates where conventional homes typically consume 6,000 hours to 10,000 kilowatt-hours. The extreme efficiency levels demonstrate what sophisticated passive design can achieve when climate, site, and design align optimally. The examples inspire similar applications where circumstances permit while providing realistic performance targets for comprehensive passive solar homes. The environmental implications of widespread Trombe wall adoption would be substantial across climate zones where the technology suits local conditions. Reduced heating energy consumption across homes with appropriate Trombe wall installations would reduce associated fuel consumption and emissions. The aggregated environmental benefits scale with adoption across populations of suitable homes, potentially producing meaningful regional environmental improvements through individually modest interventions. Utility energy efficiency programs and governmental incentives increasingly recognize passive solar strategies, including Trombe walls, as legitimate efficiency approaches deserving support alongside active renewable and efficiency technologies. The retrofit considerations for adding Trombe walls to existing homes involve evaluating whether existing south-facing walls can accommodate the addition and whether project economics justify the construction investment. Retrofit projects typically involve adding glazing systems to existing south walls while upgrading wall surfaces for optimal absorption characteristics. Some retrofits require new wall construction, replacing existing walls with massive alternatives. The retrofit complexity and cost vary substantially based on existing wall conditions and desired design outcomes. Careful analysis helps homeowners evaluate whether retrofit applications suit their specific circumstances. The aesthetic considerations affecting Trombe wall acceptance include both the visible glazing element, exterior appearance, and the interior treatment of the massive wall surface. Exterior glazing can be integrated with architectural character through framing details, proportions, and relationship to adjacent building elements that minimize visual intrusion while maximizing solar performance. Interior wall surfaces can receive decorative treatments compatible with desired interior aesthetic while maintaining heat transfer characteristics through careful material selection. The aesthetic flexibility enables architectural integration across diverse style preferences beyond purely utilitarian visual appearance. Felicity Masterton-Kowalski, an interior designer specializing in passive solar home interiors across Colorado and Utah, has developed decorative approaches for Trombe wall interior surfaces that maintain thermal functionality while producing aesthetically appealing interior character. Her design portfolio shows how massive wall surfaces can become distinctive interior features that homeowners value for their visual character alongside their thermal contributions. The integrated aesthetic approach demonstrates that passive solar homes need not sacrifice interior design quality for performance benefits. The design work expands the acceptance of Trombe wall applications among homeowners concerned about aesthetic implications. The construction sequencing for Trombe walls in new construction differs from conventional wall construction in ways that affect project planning. The massive wall construction typically proceeds early in project sequencing to provide structural foundation for subsequent building elements. The glazing installation can occur at various project stages, depending on specific design approaches. The interior finishes wait until building weather protection permits interior work. The ventilation controls and finishing details complete near project completion. Understanding the sequencing helps project planning and scheduling that accommodate the specific requirements of Trombe wall construction within overall project timelines. The educational applications of Trombe wall examples in architectural and engineering curricula demonstrate passive solar principles through concrete illustrations. Design studios assigning Trombe wall projects teach students to integrate multiple considerations, including solar radiation, thermal mass, architectural integration, and building systems coordination. The pedagogical value extends beyond the specific technology into broader understanding of integrated design principles that serve students throughout their subsequent careers. The educational integration contributes to professional development that benefits the broader design community alongside individual student growth. Consider what Trombe wall technology means for appropriate residential applications. The sophisticated passive heating provides substantial portions of annual heating needs through thermal management of solar input without active equipment requirements. The integration with other passive solar strategies produces comprehensive approaches to reducing auxiliary heating needs substantially. The durability of massive wall construction exceeds conventional construction substantially, providing centuries of service with minimal maintenance. The environmental benefits include reduced heating energy consumption and associated emissions across extended operational periods. The design sophistication required for optimal implementation limits applications to projects with appropriate architectural and engineering expertise. The climate suitability constraints favor applications in regions with substantial winter sunshine and real heating loads. The architectural integration requirements affect design flexibility in ways that matter for project planning. The operational engagement required for optimal performance may not suit all homeowner preferences. The construction costs exceed conventional alternatives substantially, despite favorable life cycle economics. The question isn't whether Trombe walls deserve consideration for appropriate applications. The question is how designers and homeowners can identify opportunities where climate, site, and project circumstances align to support successful implementation. The answers involve systematic analysis of climate suitability, site solar access, architectural integration possibilities, and homeowner preferences for active engagement with passive system management. For any homeowner or designer considering passive solar heating strategies in suitable climates, Trombe walls provide proven technology worth serious evaluation alongside alternative passive solar approaches that may or may not fit specific circumstances equally well. The monitoring and performance verification approaches for Trombe wall installations help document actual performance against design expectations. Temperature monitoring at multiple wall surface locations verifies thermal management patterns across daily cycles. Energy consumption tracking for auxiliary heating quantifies actual heating reductions from passive solar contributions. Comfort assessments from occupants document whether heating delivery patterns match occupant preferences and schedules. Professional commissioning services provide systematic verification that completed installations perform as designed, identifying and addressing any issues that prevent optimal performance. The monitoring and verification activities support ongoing operation alongside initial commissioning. The emerging research into hybrid passive-active systems Combining Trombe walls with complementary active technologies represents interesting development direction. Small photovoltaic arrays integrated with Trombe wall installations provide electricity generation alongside thermal heating. Heat pumps supplementing passive heating provide flexibility across varying conditions when passive alone proves inadequate. Thermal storage expansion through phase change materials or expanded mass capacity extends Trombe wall contributions across longer cycles. The hybrid approaches combine the best capabilities of multiple technologies for performance exceeding what any single approach achieves, while leveraging the substantial passive foundation that well-designed Trombe walls provide. Isabella Fernandez Morales, a renewable energy researcher developing hybrid system concepts at a Mexican university, has documented how combined Trombe wall and photovoltaic systems produce buildings approaching net zero performance in appropriate climates. Her research buildings demonstrate how sophisticated integration of multiple technologies produces results impossible through any single technology alone. The research directions suggest future development trajectories that will likely expand Trombe wall applications through integration with complementary technologies, rather than replacement by alternative approaches alone. The long-term operational experience across decades of actual Trombe wall installations provides valuable real-world evidence supplementing theoretical analysis. Homes with properly designed Trombe walls installed during the 1970s passive solar era continue operating successfully today, demonstrating durability and reliability that theoretical analysis alone cannot validate fully. The long-term owners of these installations provide valuable accounts of ongoing operation, maintenance requirements, and performance patterns that inform contemporary understanding of realistic expectations. The accumulated operational experience represents important intellectual resource for designers and homeowners considering contemporary applications of the technology. Grayson Holloway Pinchbeck, a home inspector who has evaluated numerous passive solar homes built during the 1970s and 1980s across New Mexico and Arizona, has documented the long-term condition and performance of older Trombe wall installations. His inspection reports show that properly constructed installations maintain their performance characteristics across 40-plus years of operation, with only routine maintenance addressing glazing seals and ventilation mechanisms. The durability demonstrates that early investments in passive solar construction continue delivering benefits decades later, validating the life cycle economic analysis that proper project planning should emphasize. The continued operation of these installations across multiple decades of varying energy prices and technology alternatives validates the robustness of passive solar approaches that depend on physics rather than specific product markets or supply chain availability for continued function.